We will wait for a few minutes to start. Okay, let's start. Good morning and good afternoon, good evening, everyone. Thank you for all for joining from different time zones around the world. Today we'll look back at the incredible missions, share the outcomes of this year's competition, and celebrate the achievements of all teams who participated in ARLISS 2025. So let's begin with a quick overview of today's agenda. We have around 20 presentations today. And we have two sessions, first half and second half. After each section, there will be short intermission, 10 minutes. Finally, we'll close with award ceremony. Okay. Each presentation will be 4 minutes long, and please share your own screen if you need when it's your turn to present. Next, let me explain about voting form. I shared voting form link on the chat. Do you have link, voting form link? Okay. This voting should be done by one representative from each team. For each evaluation category, please rank the teams from first to fifth. So we have 5 evaluation category. So you need to check whole category every time. Okay, do you have any question for voting form? Okay, we have a lot of presentation today, so we don't have time. So let's get started with presentation of SuperNOVA.
Okay, I prepare. Can you see my presentation?
Yes, I can see it.
Okay, let's start. Hi, we are Tokyo University of Information Sciences Team SuperNOVA. Let's start presentation. I'll show you a feature of the concert. The mission is decode the goal coordinates from the arc marker IDs and achieve a geometry goal using object detection and LiDAR. The concept these multiplies IDs from arc markers. Each from the correct and incorrect goal positional coordinates by dividing the coordinates data by the marker ID. This mission is the same as the rules for the totally robot challenge final one. Use object detection, recognize the goal and navigate close to it. Use 2D LiDAR to measure distance from the goal determination. It can ride go to the while measuring the actual distance. I'll explain the result of the first round. The consultant is 3.7 km from the goal. The concept rolled over and got stuck. Concept stops 2.2 km from the goal. I'll explain the result of second flight. This is the resulting video. Kansas landing 1.8 km from the goal. Kansas successfully departed from the parachute and Kansas ran to the goal. Kansas decoded from first arc marker. It decoded the second arc marker. It decoded the third arc marker. Successfully decoded the goal coordinate and moved toward the goal. Kansas started the goal recognition with LiDAR and measuring distance and object detection. And Kansas achieved the geometry goal. This is image log. The Kansas decoded arc markers and detected the goal using object detection and achieved geometry goal. The right figure shows the landing path. Kansas ran from 1.8 km to 0 meter. Their being time was about 1.5 hours. Finally, I show result of my success criteria. Full success is a decoded arc marker and reach within 10 meters from the goal. The second flight was full success, achieving a 0 meter landing on the goal. Extra success is achieving 0 meter goal with object detection and LiDAR. But the concept drive to the goal determined the goal was reached using only object detection. Extra success was vertical achievement. That's all. Thank you, ARLISS official, and thank you, Aeropax, and thank you, ARLISS all member. Thank you for listening my presentation.
Thank you, SuperNOVA. Before we move on to next thing. We have another regarding stuff for voting form. You may not vote for your own team. You have to vote another team. Okay. Next team is DOMAKU from Institute of Science Tokyo. Team DOMAKU, okay.
Okay, can you see this slide?
Yes.
Okay. Hello everyone. Thank you for this opportunity. We are Domak from Institute of Science Tokyo. Today, I'll report the result of our CONSAT mission. First, I'll explain our mission and its purpose. Our mission is to demonstrate a deployable dome mechanism that can protect sensors and electronics after landing. Dust storm and dust debris on Mars pose serious threats to rovers and astronauts. A small self-deployable dome can provide dust protection and thermal stability for future planetary missions. In this mission, we aim to deploy a 1-meter diameter dome from a Kansas-sized system, serving as a temporary shelter for rovers or astronauts. The system was designed to verify the feasibility of the deployable dome mechanism after landing. It mainly consists of two mechanisms, uprighting and dome deployment. The uprighting mechanism shown in this video uses a spring to rotate the body upright after landing. The side spring pushes the body upward until it stands vertically. Next, the dome deployment mechanism expands the membrane using a shaft and ring structure. The shaft is ejected upward by a spring, and the film spreads to form a dome shape. Next, I'll talk about the flight results, including both the first and second launches. In the first launch, the launch separation and parachute deployment were successful. However, post-landing mechanism did not activate. External wiring was damaged, and the parachute convex slipped under the body, preventing separation. These issues were analyzed and we improved wiring protection for the next flight. In the second flight, the launch and landing were successful again. No visible damage or disconnection was found after landing, confirming that the mechanical improvement worked. However, the mechanism still did not activate. After recovery, we attempted to deploy the dome, but it did not fully deploy. The full sequence until landing was achieved twice. The structure remained intact, showing mechanical robustness. The mechanism didn't work as expected, but we learned a lot about failure analysis and system reliability. From the two launches and the overall concept development, we gained many valuable lessons. These challenges gave us practical knowledge and strengthened our teamwork. We will make use of this meaningful experience in our future university project. That's all for our presentation. Thank you for listening.
Thank you, Domaku. Okay, next we'll have Kishin, Jushin, Doshin from Institute of Science Tokyo.
Okay. Can you see my slides?
I can see it.
Okay. We are Aichi, Jushin, Doshin. We will begin our presentation. First, we will explain background of our mission. For future planetary exploration and human settlement, surface bases are essential. In base construction, it is necessary to obtain information about the ground conditions, such as soil hardness, presence of voids and layer structure through wide area ground surveys. Such information can be obtained using a ground survey technique called the surface move method. We focus on this surface move wave method. The surface wave method involves installing 24 to 48 geophones sensors that output voltage in response to ground vibrations at equal intervals, and the geophone detector impacts generated manually with a hammer. Considering the limited resource of our concert, we decided to demonstrate the key technologies necessary to implement the surface wave methods on planetary surface. Deploy the sub-module equipped with a geophone, apply multiple impacts to the ground, record the voltage output from the geophone with timestamps on micro SD card, and transmit the data to the ground station. To summarize, our mission is demonstration of key technologies for implement the surface wave methods in planetary base construction. Next, we will explain mission section of our concept, starting with how to impact. Multiple impacts are applied to the ground by lifting and dropping the entire main module using cylindrical mechanism. Both impact and stowing are achieved by forward and reverse rotation of a single motor. Next, we will explain the sub-module equipped with a geophone. The geophone's output voltage is converted to digital signal via ADC and recorded on a micro SD card at over 20 Hz, while the data is also transmitted to the ground station. The sub-module separates from the main module by summary cutting two tether lines. Finally, we will talk about mission achievements. We successfully completed 11 out of 14 mission items. Minimum success was defined as completing all mission items, while full success was achieved if the main module could move to the first impact point. We are satisfied that our thorough preparation led to these results. This concludes our presentation. Thank you very much for your attention.
Thank you, Kishin, Jushin, Doshin. Let's move on to the next team, Team Wolve'Z from Keio University.
Can you hear me?
Yep.
So, let's start the presentation. Okay, so hi everyone, nice to see you all here. Today I'm going to talk about the ARLISS2025 result on Keio team of Wolve'Z. First, I will explain the background of our mission. The Japanese government is planning remote or autonomous lunar-based construction using robots to lead the world in lunar development. For humans to live in an unmanned base, food production must be completed before their arrival. If food is ready in advance, humans can begin activities immediately after landing on the moon. Our mission is titled Autonomous Rover for Uniform Seed Sowing in lunar farms. In this mission, assuming the environment of a lunar base, the rover carries out straight-line seed sowing at equal intervals toward the landmark, and we use image-based navigation because considering GPS unnavigable in the moon, and sow seeds at the equal intervals toward the landmark, and it becomes easier to manage crops. Our mission is divided into 4 parts. Minimum success is landing and deploy parachute and soft landing. And release the landmark, it is installed at the sub-carrier and the operation check and moving. The middle success is sowing seeds. It is landmark searching and recognize the landmark and move the sowing seeds position and the sow equal intervals. Then we verify the distance between the seeds to check if they were sown evenly, and this is the first success. And the advanced success is running to the goal using GPS and the camera. Our key point of mechanism is sowing. Seed sowing process is divided into 2 parts, drawing operation and seed release. Our mechanism enables these 2 movements with a single servo motor made by 3D printed geared mechanism, like shown this movie. Next, software. Landing judgment is done by 3 sensors: acceleration, time, pressure. And reaching our marker is done by like this algorithm showing this movie, and using color recognition and air detection and moving. And sowing seeds is rotate the servo motor once for each seeding, and using the distance from the AR marker to maintain equal spacing. Finally, success judgment is evaluate the linearity from a top view using projective transformation and ransack. Result. First launch, the result was unfortunately failed. The cause was a tire broken due to the shock of landing, and GPS broken due to the vibration. So we improved the attach a sponge to a tire as a shock absorber, like this, and fix the GPS with a glue gun. Second launch, it was a minimum success. It opened its sub-carrier, however, it completely stacked while sowing. So improvement for next year is to improve the tire shape, not to stack. So this is a summary, and thank you for all of you, including AirPack members, management team, and all the members who participated in this experiment. Thank you.
Thank you, Team Wolve'Z. Next, we'll have TDU presentation.
Okay, just meet. Can you see it?
I can see it.
Okay, let's go. Hello everyone, I'm Suemori from Team Don't Rest Uncharted. Today, we introduce the ground effect concept, a launch coding system based on the coordination of heterogeneous robots. Recently, concept designs have largely converged on 2 types: two-wheeled robots and drones. We consider this a very serious situation. Where has our spirit of challenge gone? Where is innovation? Then we had an innovative idea and put it into practice. Look, down in the ground. No, it's a here. We have the first, beyond robots and drones, the first ground effect concept. The left is experiment movies, and the right is camera view attached to the concept. And the ground effect concept reaction propulsion with adapted fan, enabling high-speed movement, the ability to jump over that. And then we called it ARLISS. The hacking set, small and light, acquires topographic data using a Sony's presence, and boasts superior off-road capability with its measured tire. And then we called it B-parts. We made many types of ground effect concepts. First, second, third, and finally. This slide shows the end-to-end flow of our launch decoding system using two heterogeneous robots. On the left, after touchdown, the B part moves. The B part searches for approaches the A part, then sends a launch trigger. The A part receives it, boots, and takes off in ground effect flight. The result, first launch successful boot A parts, but deploy case failed because misjudgment of sensor value. Second launch, successful deploy case, but boot parts failed because battery contact failure. But the deploy case is success and boot B parts, but there is not signal in A parts. And experiments in the Black Rock Desert showed A parts could navigate floods and potentially overcome deeper ones. B parts image and video from the second launch was clear, confirming successful recording even when inside the case. This result shows that a specialized system of A and B parts can accomplish the mission, which means a more flexible rover can be built for ARLISS competition. Finally, we would like to express our sincere gratitude to all the sponsors, team members, and everyone involved in ARLISS 2025 as well as to AirPack. Thank you for your listening.
Thank you, TDU. Let's move on to the next team, MultiTMU from Tokyo Metropolitan University.
Okay. Okay, can you hear me?
Okay, you share not full screen. Can make it full screen.
Okay. Please wait a sec. Full screen. presentation. Okay, sorry. Good morning. We are MultiTMU from Tokyo Metropolitan University. Today, I will present our mission results using our multi-IMU technology for autonomous navigation. Why do we need multi-IMU? When exploring the moon or Mars, we face three critical challenges: no GPS satellites, no magnetic field for compass navigation, and confined spaces like lava tubes. Our multi-IMU system provides radiation tolerance and continues working even if some sensors fail. Our mission target is simple but ambitious: multi-target approaching using multi-IMU-based guidance and control. This means our rover can autonomously navigate to multiple targets without any external positioning systems. Here's our mission sequence. The key moment comes at step 10. We switch to multi-IMU that we made a navigation near the goal for precision approach. This allows us to navigate through ruts and reach both the traditional cone target and the new full ball goal. Our CANSAT is a compact autonomous rover featuring multi-IMU as the core navigation system. We use STM32 for processing and specially designed 3D printed wheels for rough terrain. So what exactly is multi-IMU? It's an array of 32 IMU sensors achieving low noise reduction through statistical fusion. The module provides standalone position estimation. No external references like GPS needed. Here we demonstrate multi-IMU's robot navigation. On the left, watch as we drag paper under the rover. Despite this disturbance, it still reaches the 1 meter target accurately. On the right, rover continuously tracks 1 meter square path, proving our system's precision and lack of drift over repeated cycles. Okay. This shows our approach sequence to a traffic cone. The rover progressively approaches from 8 meters to 70 centimeters, then 30, finally reaching the target. Each step demonstrates multi-IMU's precise distance controls capabilities. For the new full ball goal configuration, our rover successfully navigates between the balls, approaching from 50 centimeters to reach the center point, a challenging multi-target navigation task. So let's look at the first launch. In our first launch, our CANSAT successfully detected separation shock and deployment shock. All three pressure sensors logged data throughout descent. Landing detection worked perfectly. However, post-landing, the parachute caught wind and dragged our CANSAT, causing motor damage. Peak accelerations exceeded 10 G multiple times. Second controller, due to software issues, forcing mission retirement. But there is the exciting part. Since hardware remained functional, we initiated navigation from the landing site. Fortunately, the goal was only 1 kilometer away. We successfully reached the goal. Our conclusion shows strong validation of multi-IMU technology. We confirmed the noise reduction, survived shocks, and our stack detection worked perfectly. While we identified areas for improvement in software and communication, the core multi-IMU technology is proven and ready for GPS-denied exploration missions. Thank you for listening. We express special thanks to ARPAC and the ARLISS management team for organizing this amazing competition. Thank you. We were multi-IMU. Thank you for listening.
Thank you, MultiTMU. Let's move on to TMU Beacon. Can you see it? Yes. Okay. Let's start presentation. Hello. We are TMU Beacon. We are a team of 8 B3 students and worked so hard this project year. Now I'm going to explain our project. First, mission background. Many of the concepts use GNSS for navigation, but GNSS cannot be used on planets. In the past, there were some cases where structures installed in advance. So we assume the planetary exploration, the mission must be accomplished with a one-time launch. So our mission statement is building a beacon system and guiding the rover. This is mission sequence. First, releasing from the carrier. Second, deployment of the deceleration mechanism. Third, landing. So, creating a beacon system and guiding the rover. Next, I will talk about features. It is possible to estimate the distance by measuring how much the radio wave strength has attained out between the transmitter and receiver. Mapping of the entire field into a two-dimensional orthogonal coordinate system is possible by establishing mutual communication among 3 or more vehicles and utilizing the rover's IMU. Next, we installed 2 beacons and a rover in rocket. Several beacons are installed ensuring redundancy. Also, this serves as a landmark for following proofs. We developed new deceleration mechanism. Please look at this picture. It has 6 wings mounted around the beacon. Please look at this movie that shows the process of free fall. Next, this is the beacon we developed. It decelerates by rotating like a helicopter. There are 2 advantages. First, it can land the desired posture, this point upward. Second, it is not dissipated by the wind, so there is no longer a need to install a parachute separation mechanism. Next, I talk about competition results. Ground station has established communication with all aircraft, and the rover received signals from 2 beacons and acquired RSSI values. At the first launch, the parachute failed to separate, but on second launch, it separated successfully. Also, we were able to run the beacon pointing upward on the second launch. In this way, we identified the issues during first launch, and we were able to achieve good results in second launch in a short time and with limited materials. From ARLISS2025, we learned these lessons. Cooperation and legacy are key to solving problems, and ignored or unsolved troubles are inevitable. That's all for our presentation. Thank you for listening. Thank you, TMU Beacon. Let's move on to Georgia Tech. Georgia Tech, are you in this meeting?
Yes, sorry, 1 second.
Okay.
Okay, can you see my screen?
Yes, I can.
Okay. I'm presenting for Georgia Tech. Our mission statement was kind of based around the fact that this is our first time participating, so we just wanted to make a robot that could show up and work and survive, and we just based it on a simple rover design that we saw was common in other previous years. And we're also doing this on a tight time frame, so we try to keep everything as simple and basic as possible. A little overview of our design is just mostly 3D printed structure with PCB, battery, parachute mount, and then a tail, and then the wheels would kind of fold in over the robot so they could fit together. Our first attempt, we retired because the parachute fell directly on top of the robot and got tangled up in the wheels, and then it just kept getting worse and worse because the wheels were trying to move. And we believe this was mostly due to low ground winds at the time of launch, and also our parachute line was quite short. And then in our second attempt, we had multiple failures in our structure at a motor mount and at the stabilization tail, and our GPS module failed for an unknown reason. And we also, on both attempts, we had trouble getting in contact from the ground station to the robot while it was in the air with radio. Here's a video of the results from the first attempt. So as you can see, everything worked except the parachute just fell on top of the robot, and it released the parachute too. A couple problems we ran into were we had trouble getting the robot into the payload, our radio communication was spotty, and the structure wasn't as robust as we thought it was, and our controller wasn't as intelligent as we needed it to be. And these are all things we're going to improve next time around. Our success criteria, our minimum success criteria was to land with everything intact, which we reached. In our first attempt, our full success was to actually move once we land, which we didn't reach. And then extra success would have been reaching the goal within 10 meters for us. I just want to say thank you to the AeroPack and ARLISS2025 members, and then the sponsor that actually helped us get out to the desert. And well, that's all I have.
Thank you, Georgia Tech. Next, we'll have Cocles presentation.
Yes. Okay. Just give me 1 second. Can you see my screen?
Yes.
Yes. Okay.
Good evening, everyone, and good morning for Japan and Korea. It is a pleasure to be here representing our team Cocles with our device, Diburo, for the ARLISS project. Our team is composed of 10 dedicated students who have worked together to design, build, and prepare our project for this year's ARLISS presentation. Each member has contributed their unique skills and expertise to make this possible. Today, we will be sharing an overview of our project, including its objectives, design process, testing, and expected outcomes. Our mission was to develop a portable self-rescue device that records trajectory, transmits critical data, and in emergency situations, facilitates the user's location, heart rate, blood oxygen, and rescue in remote areas.
For our design and systems, this is the first year we are participating with a drone, So we decided to use a commercial off-the-shelf drone stability and motor control. However, we designed our own mission controller PCB. This is our finalized drone design. It folded in itself, and the idea was that the motors would unfold when the drone reached the ground. This is some images of our final drone. As you can see, here it is folded inside of its protective wrapper for landing, and then we have it fully extended. These are the two modes of it. We do this so it can fit in the rocket payload. Then, we had some preliminary tests in order to verify that the drone was flying correctly. We had some issues, as you can see in the video. We had a pretty bad crash one time. Some of them were chassis rigidity. We found out that for a drone to be stable, the control system assumes that the chassis is rigid, and the chassis wasn't as rigid as it needed to be initially. Then we had some issues with part strength. This was fixed by increasing the 3D printed parts as infill and wall count. And then part of the chassis rigidity issue, our motors were overheating since they were having to compensate so much and so quickly. So that also became an issue. But we finally managed to fix most of them. The control system, we just reduced some gains and finally.
Okay, problems and solutions. In the desert, part of the drone's chassis is cracked. We repaired it with epoxy and fiberglass reinforcement. Next, please. Results. We did only one flight. After the drone separated from the rocket, the protective shroud tore at some point in the descent. So the drone fell without parachute and the proper protection. This caused damage to few external parts. However, the electronics and the software kept working, and the arm release mechanisms also functioned as planned. So we considered minimum success. We found the parachute with the protective shroud at a considerable distance from the landing point. In the ARLISS project, we learned valuable lessons about experimentation and materials. We worked with nylon and carbon fiber for the first time, and even created our own springs with heat treatment. These experiences taught us how materials behave under different conditions and how every challenge is an opportunity to improve. In the end, ARLISS showed us that true engineering is built through teamwork, creativity, and constant learning. Thank you so much.
And that's it for us. Thank you.
Thank you for your presentation. Let's move on to Morpho.
Yeah. Can you let me know if you can see my presentation, please?
I see something like
Let me see.
We're seeing Canva.
Oh, okay. But you didn't see the specific. Okay. I think it's this one. Not yet.
no, I can see it.
Okay, perfect. Well, it's a pleasure to be here. Thank you for the invitation. And we are the second team representing Costa Rica this year from the Universidad of Costa Rica, and our team name is Morpho. Specifically, our candidate's name in this case will be Eleanor. In the picture, you can see four of us at the desert, but in reality, we are around a team conformed by around 9 people. Let me see. Okay. Now, in this slide, you can see our mission. As you can read, it says that our mission in general was to develop a CANSAT capable of delivering a payload to a specific location, meeting all the requirements established by the ARLISS competition, such as the dimensions and the weight. Here you can see some, our CONOPS, in which the mission started at the moment that we introduced our CANSAT in the rocket. And as I said, our mission was to deliver a payload at the coordinates given by the management team before we charge the rover in the rocket. So at this point, I would like to divide into our success. First of all, partial success was that our CANSAT could land and didn't receive any type of damage that could make him drive or move to the coordinates. And a complete success would be get to the coordinates and deliver the payload that in this case was a box of 5 centimeters from each side. These are some pictures of a rover or CANSAT in Costa Rica. We were divided in 3 different sections, which were mechanics, electronics, and the algorithm section that was in charge of the code. In the mechanics section, as a summary, we were in charge of designing all the components of our rover, such as the wheels, the frame, and the grappling system that we were going to use for our recovery system. In the electronics section, they were in charge of designing the PCB and the communication in land, so we could receive any kind of information and see how our rover was doing in the desert. And the code section was we were lacking in that section. To be honest, it's something that we have to improve for next year. And as you can see in this video, this was a test that we did the day before our second attempt. Our CANSAT was moving really good, and the design in general was reacting fine to the desert conditions. We were doing 2 attempts. This picture that you see right here was the first attempt in which our grappling system failed, which led to a free fall from around 2,000 meters. And when we find our CANSAT was in these conditions, all the design, all the components survived, but it could not move from there. As I said, we were going to do a second attempt, but when we were building a rover, something failed in the electronics, so we couldn't fly our second attempt. Like I said, aspects to improve. This year was full of, we learned many things, in which for the next years, we would like to improve our recovery system of the parachute, the wheel attachment mechanism, attachment of the parachute to the grabber, and the assembly of the components. That will be it. Thank you very much to AeroPack and the ARLISS management team, and hope to see you next year.
Thank you, Morpho. Okay, then let's move on to HERMES.
Hello, can you hear me?
Yep.
Okay, so 1 second, please. Okay, so hello, we are Team HERMES from South Korea. Our vision was to conduct a humanistic experiment in which questions collected before rocket launch were transmitted to the ground via a CANSAT using LoRa communication. The CANSAT's mission was the collected questions are transmitted to the ground via LoRa. As a result, the rocket ascended to 3.3 kilometers and we successfully recovered the CANSAT. We also confirmed in real time from the ground station that the questions were successfully transmitted via LoRa. Additionally, we attempted to record video using GoPro, but unfortunately, this part was unsuccessful. The reason we placed embedded questions inside the rocket is that we believe communication problems in modern society can only be solved by when people start feeling genuine curiosity about others through questions. Two questions were embedded in the rocket. What is the question you consider most important in your life? And the second question was, what question would you like to live for humanity 1,000 years from now? We first asked these questions to several well-known figures. Among them were Dr. James Green, who is former chief scientist of NASA, Lee So-yeon, the first astronaut of South Korea, and Tim, the CEO of Apogee Rocketry, who many of you may know. So Dr. James Green asked, does life exist beyond Earth? And what new technologies have changed the way humans view the universe? And also Tim from Apogee asked, do I have the ability to inspire people's passion? And have you left enough resources for the next generation? In addition, questions from many students and professors at our university were also stored in the CANSAT and successfully transmitted to the ground. This project can be seen as a form of performance art, blending technology, philosophy, and human curiosity. Lastly, let me share the future plans of our Sungkyungwan University rocketry team. During this ARLISS competition, we were deeply inspired by the pure passion for rocketry shown by the Aeropex staff, ARLISS staff, and patients and many flyers. We were truly impressed by their technical excellence. While our club's current focus includes CANSAT missions, we were also dedicated to developing our own launch vehicles. So our next goal is to design and build a rocket capable of exceeding a 3-kilometer apogee through our own efforts. If possible, we hope to return to ARLISS next year as a flyer team to launch our rocket carrying same philosophical questions once again. We wish to continue this mission annually, and we would like to say special thanks to Aeropex staff, ARLISS staff, participants, and all flyers who made this incredible experience possible. Thank you very much.
Thank you for your presentation. First session is done. So let's get a break. We have 10 minutes to take a rest. See you in 10 minutes. Time is up. Come back to this meeting. Let's get started. Second session. We have STELA presentation.
Okay, my name is Yoshitsune Oshiro from AUT. Our mission is achieving a 0-meter goal using GPS in the new goal system. The reason we set this mission is that we have not yet achieved the 0-meter goal. In future development, we aim to build a technical foundation that can be expanded to other missions, with the first step being the success achievement of the 0-meter goal. First, the CANSAT is stored in the carrier and rotated into the rocket. Second, launching by rocket. Third, the ascent is detected by the pressure sensor. Fourth, after being released from the carrier. The CANSAT that communicates wirelessly with the ground station piece and transmits GPS coordinates while descending with a parachute. Fifth, after landing, the parachute is detached. Sixth, preparation for driving and start of movement. Seventh, drive towards the target coordinates. Eighth, task detection and red color recognition. 9. After reaching the target coordinates, move towards the center coordinates. 10. Using GPS drive to a point within 3 cm from the center coordinate to reach the goal. 1. From launch to rendezvous. Minimum success decelerated by the parachute. Full success detects ascent with the pressure sensor. Extra success detect descent using the pressure sensor. Transmit GPS and the parachute. Second, driving. Minimum success after developing the front and back arm. Completing the preparation for driving, begin driving. Full success stop just before the new goal. Extra success travel to the goal coordinate and achieve the 0-meter goal. During the tow launching, the wheels came off and the parachute wheel to separate from the body. During the first launching, we were able to obtain our pressure data showing ascent and descent. However, the mission ended because the separation from the parachute failed. I would like to express my gratitude to Airpark and the entire operations team. Thank you.
Thank you, Stella. Let's move on to Avispa.
Can you hear me?
Yes, I can hear you.
Wait a moment. That's really great. Mm, mm. Can you see the slide?
Yes, but it's okay.
Okay. Good morning and good evening, everyone. We are Avispa from the University of Tokyo. Today we'll talk about constant mission and ARLISS result. Our mission is to achieve 0-meter goal by multicopter. As shown in this image, our concept is loaded on the rocket, launched, released in the sky, land to the ground, and fly to the goal. This is our concept. It is a multicopter with 4 rotors. Flight controller and onboard computer is on board for processing information and controlling the flight. And various sensors are on board for mission as well. Our concept has standing up module. Standing up module is designed to make our multicopter upright when it is landed, so that it can easily take off. Next, I will talk about the results of our ARLISS launches. We conducted 2 launches. In the first launch, we lost visual contact with the vehicle immediately after liftoff. The concept was eventually found near the rocket, with the 2 arms heavily damaged. From this, we believe it went into freefall. On the other hand, the electronics were still working, so we were able to analyze the logs. We summarize the log analysis in this table. As you can see, it shows that the deployment occurred while still inside the rocket. From this, we concluded that the failure was caused by the timeout being too short, because we hadn't fully accounted for the significant launch delay. Our countermeasures are making sure to thoroughly check the sequence before launch, reviewing the sequence with the entire team, not just the control team. In the second launch, the concept landed without damage, but didn't deploy. Log analysis showed that the Raspberry Pi program has stopped due to the signal handle error. We think that for some reason, the Raspberry Pi's power supply was momentarily interrupted, causing it to reboot and stop the program. We also checked the voltage log of the Pixhawk, which shares the same power line as the Raspberry Pi. This log shows that the Pixhawk didn't lose power. From this, we suspect that there was likely a poor connection between the Raspberry Pi and the board. This summarizes our result in terms of the success criteria. Some of the minimum success criteria were achieved, while others were not. We very appreciate the AirPad team and ARLISS managers. Thank you very much for your attention.
Thank you, Avispa. Let's move on to SEIKOKU.
Good morning, everyone. Can you see the slide?
I can see.
Thank you. We are Team SEIKOKU from the University of Tokyo. Oh. Let's begin with the mission overview. Here is mission overview. Our mission statement is autonomous pinpoint guidance by a drone. Precise landing is vital in future space missions. Like in Hayabusa 2, touchdown carries high risk for the spacecraft. So small autonomous landers with precise control are expected to play a key role. This is a mission sequence. After landing, the CAN stands up so the multicopter can take off. It then flies to the goal by GPS, and near the target, the image navigation system takes over for a precise landing. To achieve this, we focused on reliable and reproducible development. Our policy had 4 points: reproducibility including operation, test-based design, and day one morning launch to use calm wind conditions, and strong documentation to reduce dependence on individuals.
Okay, then I'll explain the details of what we made. The total weight is 1,045 grams, and the estimated flight distance is 8.1 kilometers at a speed of 7 meters per second. Our CANSAT consists of 2 parts, the self-righting mechanism and the flight mechanism. The self-righting mechanism stands the flight mechanism vertically with spring force, regardless of its posture after landing. The flight mechanism is made up of a PLA CF body and aluminum pillars. This configuration provides high rigidity and minimizes vibration during flight. And there are 2 key features in terms of control. First, we used a simulation system provided by Hakoniwa. We used it to validate our control algorithm before the actual flight test, which helped prevent any damage to the real machine. Second, we implemented a redundant system design. LiDAR was used as backup for altitude measurement when the GPS malfunctioned, providing an independent source of data. In addition, we implemented a retakeoff sequence to recover from fail-safe activation caused by sensor malfunctions. And here's a video showing the image navigation sequence.
Next, I'll show you our results. We made 3 attempts. On the first launch, we had to retire, but we achieved the first launch of the competition, which had been our development policy. CANSAT took off and flew 1.25 kilometers, but stopped because the main computer froze. We found that an asynchronous coding error caused this, and we fixed it for the next. On the second attempt, the main computer rebooted unexpectedly, caused by a shock during rocket release, according to the logs. We hadn't prepared an auto restart, so the mission ended. On third launch, maintenance errors made the GPS cable disconnect during takeoff, forcing an emergency landing. Finally, let me show you another flight results. We reproduced the third attempt using the same starting point and distance. It could fly for 12 minutes, and the image navigation partly succeeded, and the CANSAT landed 87 centimeters from the goal.
finally, these 3 points are lessons we learned. So first, we have to prioritize end testing, and second, we should have a postpone and test, which means the rebooting systems, and finally, maintaining a mechanical consistency of spare units was so important. That's all for what we learned.
Thank you for your presentation. Let's
Thank you
move
for
on.
listening.
Thank you. Let's move on to the next team. SARD.
Yes, can you hear me?
I can hear you.
Okay. Hello everyone, we are SARD from Muroran Institute of Technology. Today I'll talk about our CANSAT and the results from ARLISS2025. This is our CANSAT. The design theme is redundancy. It means our system keeps working even if one part fails. We used strong materials and enough space to mount several sensors to make it reliable. The body is made of CFRP and the wheels are made of TPU for flexibility. The onboard computer is Raspberry Pi 4 and we also use our 2D LiDAR. Our mission is demonstration of adaptive navigation that switches and fuses sensors according to the situation. For example, when GNSS is stable, the CANSAT uses GNSS mainly. When GNSS becomes unstable, it uses GNSS and IMU together. When GNSS is lost, it switches to IMU and performs dead reckoning. The CANSAT automatically changes which sensors it uses depending on GNSS accuracy. This is our adaptive navigation system. In the first launch, the CANSAT landed safely, but it couldn't separate from the parachute. It was dragged by the wind and retired 5.3 kilometers northeast of the goal. This launch was unsuccessful, but we found the cause and prepared for the next one. In the second launch, the CANSAT could move by itself. At first, it moved in circles and went away from the goal, but after the sensor reset worked, it moved straight and approached the goal. Finally, it stopped 584 meters away from the goal because of battery depletion. The total running distance was 5.6 kilometers, and it ran for 1 hour and 35 minutes. We call this a minimum success. We found one mechanical problem. After landing, the motor and wheel were pushed into the body, and the wheel touched the frame. This caused unstable movement in the early part of the run. This was an important finding for improving our design. From the ARLISS, we learned that both software reliability and mechanical durability are essential. The sensor switching system worked just as we planned, and that gave us confidence in our control logic. As a team, we also learned how important it is to share problems quickly and manage the project together. This experience helped us grow not only as engineers, but also as a team. For the next step, we'll improve the structure to protect the motors and pass our knowledge to the next team for ARLISS. That's all for our presentation. Thank you for listening. We are SARD from Muroran Institute of Technology. Thanks so much.
Thank you, SARD. Let's move on to next team, Noah's Ark.
Can you hear me?
Yes.
We will present a report from Team Noah's Ark of Tokyo University of Information Sciences. Our mission is to verify the accuracy of driving without using GPS and use LiDAR to detect and reach the destination. After landing, the rover gets its position once with GPS and then it moves only sensor and wheel data. LiDAR detects the goal shape and distance of 4 preset arrivals. Next, we will report on the result of the first round. Communication was lost at altitude of 2,758 meters. This was due to the communication module becoming detached because of the impact. Communication was unavailable, but all other functions were operating normally. The rover at the point 842 meters from the goal due to dead battery. All driving was conducted without using GPS. For the second launch, we secured the communication module with a glue gun and adjust rover's driving to minimize weaving. Next, we will report on the result of the second launch. The rover drove to a point 251 meters from the goal without GPS. It then used GPS to move toward the goal, detect the goal using LiDAR, and stopped. The result was 2.84 meters. This is the travel path. Our success criteria are as follows. We achieved minimum success and full success. In the future, we aim to achieve 0-meter goal using LiDAR, and when driving without using GPS, apply corrections using this driving record. Thank you very much to AirPark and the management team. Thank you for listening.
Thank you for your presentation. Next, we'll have Mark 1.
Okay, can you hear me?
Yes.
Thank you. Sorry. No, this is not. Sorry. Sorry, please wait. Just a moment, please.
Okay. Can you show this presentation slide?
I can't see it.
Okay. Can you show?
It's
Right?
perfect. It's perfect.
Yeah, thank you so much. So, hello everyone. Today I would like to present the result of our concert project, Mark 1. First, let me introduce our team. We are Kimura Laboratory, Tokyo University of Science, a team of 9 fourth-year undergraduate students. The development period of our concert was from April 2025 to September 2025. Our mission was titled Demonstration was of a flag detection system with illumination tolerance and its application to route guidance for material transportation. The background, challenge, and objective are as follows. For the background, we considered a future in which humans live on the moon. In such a scenario, transporting materials to lunar habitats becomes essential. Now about the mission challenges. The key points are the advantages and challenges of our mission. Advantages eliminates the needs for GPS satellites and enable easy modification of routes. And challenges sensitive to illumination conditions and need to distinguish between flags. Next, the success criteria. We divide team into two types, the mission success criteria and the project success criteria. This is our mission sequence. Now the results. We conducted two launches at ARLISS, but unfortunately the concert could not start moving in either attempt. Therefore, the minimum success criteria was not achieved. However, we were able to achieve 100% of our project success criteria if we had devoted more effort towards the 120% goal. We believe we could have achieved more in the mission success criteria as well. This photo shows the rover after the first landing. When separating from the parachute and the cause got tangled with the tires and body. We believe this was caused by strong winds. This is after the second landing. The rover fell freely from the air, and the parachute was not nearby. As a result, one of the tires was damaged, and the circuit did not function properly. This graph shows the atmosphere pressure data from the first launch. And the second flight data shows similar results. This shows the program logs before and after landing, indicated that the onboard system was running properly under impact. This is after landing. Finally, in conclusion, both launches ended without the move.
the CANSAT project was successfully completed from the construction of the rover to passing all evolutions item. This year, CANSAT incorporated many new ideas such as a redesigned goal style and a completely new tire shape, allowing all the members to truly enjoy the project. Yeah, we would like to express our sincere gratitude to the ARLISS organizers and all the sponsors who supported our project. Thank you very much.
Thank you, Mark 1. Let's move on to Buttobigumi.
Yeah. Can you hear me?
Yes.
Okay. Okay. Hello everyone. Thank you for coming today. My name is Kimura. I'm project manager at Buttobigumi at the National Defense Academy. The National Defense Academy is a school that trains officers for the Japan Self-Defense Forces, JSDF. For those who are unfamiliar with JSDF, it is the official name of Japan's current military. Today, I would also like to discuss the
Excuse me.
Oh, okay.
Your presentation is not full screen.
Sorry. Okay.
No.
Okay.
Yes, perfect.
Thank you. Sorry. Hello everyone. Thank you for coming today. My name is Kimura. I'm project manager at Buttobigumi at the National Defense Academy. The National Defense Academy is a school that trains officers for the Japan Self-Defense Forces, JSDF. For those who are unfamiliar with JSDF, it is the official name of Japan's current military. Today, I would also like to discuss the results of ARLISS and why the National Defense Academy participated in ARLISS. First, our official name is the National Defense Academy Space Systems and Technology Club, and we are founded this past February. The reason for its establishment is that the importance of space security has grown in the global situation, and within JSDF, the task of space domain awareness (SDA) is an argument priority. Therefore, it was deemed necessary for JSDF officers to also possess practical experience in space development. However, despite none of us founding members having experience with ARLISS or CANSAT development, we continued the development over approximately 6 months to participating in both Noshiro and ARLISS. Furthermore, the goal of this club is to develop CubeSat. Next, I will explain the mission statement. The mission statement is achieve a zero-meter goal using a general purpose two-wheel rover built on a custom circuit board. The reason is to minimize the potential for delays in development by targeting aircraft within the simplest possible structure, and to make it easier to compare the gap in technical capabilities between our team and others. Mission sequence is shown in the diagram. Phase 1 covers loading onto the rocket. Phase 2 covers launch through development. Phase 3 covers landing through separation. Phase 4 covers diving through the 0.5 meters before the goal. And the phase 5 covers the final approach from within 5 meters to the goal. Success criteria has been set as shown in the figure. The reason for success is defined as within a radius of 5 meters is because camera guidance could not be priority designed by the time of ARLISS main event, so camera guidance was designed as extra success. As will be detailed later, we confirmed that the first third launches achieved the minimum success and after the first launch's retirement, we could achieve the middle success 2, full success, extra success 1, and extra success 3. Regarding the first attempt, although the parachute was deployed, the first pin becomes stuck in the aircraft and lock could not be released. We determined that autonomous operation was impossible and therefore retired. However, since the aircraft sustained no damage, we confirmed after retiring that it could reach goal using GPS guidance. Another issue was come to light is that developing on how the aircraft landing it may flip over when separated. Regarding the second launch attempt, the parachute that was deployed during the first launch failed to open, resulting in a free fall and subsequent decrement. The result from the second attempt reveals that depending on how the parachute is packed, there is a possibility it may not deploy. The third launch was also conducted, but the nylon cord preventing the separation mechanism from the separating until landing snapped, causing the parachute and the aircraft to separate in midair and enter free fall. Based on the result, it has been newly determined that the nylon thread may be break due to the impact of the aircraft's release on during parachute development. Where all launches were officially classified retirements, we achieved the minimum success. The first launch resulted in a damage-free landing, and during the third launch, we established communication with the ground station after development. Actually, also this occurred after the first launch attempt was aborted. We confirmed that GPS guidance enabled the vehicle to reach within approximately 30 cents of the target radius, achieving middle success 2, full success, and extra success 2. This concludes the results reports for the team Buttobigumi. Finally, we found like to express our deepest gratitude to the faculty and the students involved in ARLISS operations, to Mike, Ted, Gary, Becky, and all the Aeropark members and associates who launched the rocket, and to the advisors of our club who have provided tremendous support for this activity. Thank you for your attention.
Thank you for your presentation, Buttobigumi. Let's move on to Red Scott. Are you in this meeting, Red Scott? How about cosmics? Project Imua, are you in this meeting? Red Scott, Cosmics, and Project Imua. Are you attending? No one is attending from these teams. Okay. If anyone from L Park is joining us right now, we'd like to invite you to say a few words. No one? Okay, let's take a rest. We have 20 minutes. See you in 20 minutes. After this intermission, we have award ceremony. See you again. 教員はちょっと今からブレイクアウトルームに招待するので、そこで、会議お願いします。Please submit your voting form. Voting form will be closed in 5 minutes. We are sorry for being late. Let's start to award session, award ceremony. I will show the slide. Let me.
Okay, I'll announcement of the accuracy award. First, accuracy award for new goal. The first place is Noah's Ark, Tokyo University of Information Science. Next, accuracy award for legacy goal. The first place is SuperNOVA, Tokyo University of Information Science. Next, Best Mission Award. First, the announcement of third place for best mission award is SARD, Muroran Institute of Technology. Next, second place for best mission award is TDU Team Doctorate Uncharted Tokyo Denki University. The last, the best mission award of first place is DOMAKU Institute of Science Tokyo. Congratulations. So these are best mission awards results. Okay. Next, technical system awards. The technical system awards of third place is MultiTMU. Sorry, the university name is different. Sorry. Sorry, team name, different team name. Sorry. At third place is TDU, Team Doctorate Uncharted Tokyo Denki University. Sorry. Please wait a moment.
Let me change team name. I'm so sorry. Okay, this is proper one.
Yes. Sorry. Next, the second place of the technical system awards first place is two teams. First, technical system awards first place is DOMAKU Institute of Science Tokyo. Congratulations. And another technical system award of first place team is MultiTMU, Tokyo Metropolitan University. Congratulations. So these are technical system awards. Please wait a moment. Okay. Next, overall winner of ARLISS
ARLISS2025 team. Okay. Yeah. So busy. So the overall winner team is DOMAKU, Institute of Science Tokyo. Congratulations. Okay. Next, UNISEC Award. This year's UNISEC Award is.
Okay, so I'd like to explain. Oh, okay. So
sorry.
I'm Tamori in Nagoya University, and first I'd like to explain the background of the UNISEC Award. So this award, the UNISEC Award, is presented to a team that may not have achieved the desired result, but has demonstrated outstanding original technical excellence, and as recognized by the UNISEC faculties. And this year's award goes to at the next page, please. Hi, TMU Beacon, congratulations. Okay, thank you very much for the ceremony. So this award ceremony, and now I'd like to conclude this final ceremony sessions, and I'd like to give a very brief closing speech. So is it okay?
Yeah.
Hi. Okay, so in this year, in this ARLISS, I'm truly delighted to see so many new ideas, original ideas, and challenges. And the students have achieved remarkable, very great results with their cancer project. Of course, not everything may have gone exactly as planned, as expected, but careful reflection on such experiences is very important. And based on today's presentations, please continue to deepen your analysis and apply what you've learned to your next cancer project. And lessons learned are extremely important. And to the IROPAC members, thank you very much for joining us today. I really appreciate your continued support and for giving us such a great opportunity through ARLISS every year. Thank you very much. Okay, thank you very much, everyone, and I look forward to seeing all of you again at the next ARLISS in the next year. Thank you very much.
Thank you very much. Okay, this is the end of ARLISS 2025. Thank you for everyone, LPAC members, ARLISS working group, and management team, and also participants, every participants. We are looking forward to see you in 2026 next year. Okay, congratulations everyone. See you next year. Bye bye.
バイバイ、お疲れ様でした。ありがとうございました。
お疲れ様です。
お疲れ様です。
お疲れ様でした。